Okay, well, my name is David Taylor, and I'm at the University of Texas, Austin. I started my lab about a year ago. I was a postdoc with Jennifer Doudna and Ava Nogales. So that is my conflict of interest statement. So I was with Jennifer Doudna, so keep that in mind. I want to talk to you today. I want to take like 100 steps back from what we were just talking about. So while I think that the promise and already how gene editing is being used is both exciting, revolutionary, and also kind of intoxicating, I'd like to take a step back and think about how these machines are actually working. And I think that that's not actually represented here. So hopefully I'll talk a little bit about that and excite you guys as why that's a area of interest to still be studied. Okay, so we've talked about this enzyme a lot today, but we haven't gotten into a lot of the details. I'm going to try not to get into too many details, but there's some things that were talked about that maybe were unclear. So when we talk about Cas9, we talk about this particular enzyme. It's a single polypeptide, so it means it's one protein. What you need in order to target it to a double-stranded DNA is a CRISPR RNA guide. So we talked a lot about guides. In the actual bug where it works, it uses both a CRISPR RNA and a tracer RNase. So this stands for trans-activating CRISPR RNA. And this base pairing between the tracer RNA and the CRISPR RNA is absolutely required for the enzyme to function. And so Martin Jinnick in Jennifer Doudna's lab did this cute trick where he created a hairpin between the tracer RNA and the CRISPR RNA. And that allows us to use now a single guide RNA, which is what most people are using in their genome engineering applications. And so importantly, this entire process of cleaving on opposing strands of the DNA is the need for this protospacer adjacent motif, and it stands for PAM. So it's NGG and Cas9, and it can be other nucleotides in other Cas9 species. Okay, so everybody lost their mind because Cas9 can be repurposed for so many different applications. This is one of my favorites that happened right around the time I was working on the structure of the enzyme. And these are two monkeys that were born with customized mutations from Cas9. And this is my favorite example because the monkeys are pretty cute, so I think it's pretty good. Okay, and so then we had people like Carl Zimmer starting to say things like, this is the biggest biotech discovery of the century, and it's going to change medicine forever. And so then you get to meet Carmen Diaz and things like that. So I talk about this now in like my lecture class, and people actually don't know who Cameron Diaz is. And I'm not that old, so. So one of the things we worked on right after Martin's discovery was understanding the structure of this enzyme. And so before any of the crystal structures were available, I actually used negative stain electron microscopy to solve structures of it in various states. And what we learned were a couple things. One is that when it is in its apo form, meaning not bound to any nucleic acids, it's remarkably flat along one direction. And so this is depicted here. When you add the CRISPR RNA tracer RNA, and so this particular case, we didn't use a single guide RNA, it creates this large-scale rearrangement within the enzyme. So this flat structure now becomes a structure where there's two lobes and there's a central channel in between the two lobes. And then that's where the target DNA binds. So the structure only changes minorly from these two forms. And so this kind of gives us the idea that actually it's the RNA itself that's inducing the activity of Cas9. So without the RNA, it's just floating around. It could float around your genome and do nothing. Okay, so then later, I actually solved a cryo-EM structure of the full R loop. And so this is actually a model that Jennifer has on her desk, and she uses it a lot. It's not actually from my structure, but it looks a lot like the structure. It was a made-up version at that time. But what happens here is, here's the PAM proximal end, so the PAM is right in here. It becomes unwound. The guide strand base pairs with the CRISPR RNA, and the non-target strand creates this R loop, and the non-target strand binds along this other face of the enzyme. And it reforms the DNA duplex here at this end, and then these two places are where the catalysis is actually happening, so the active site of both the H and H and RubC domains, which are the two domains that do the cleavage of Cas9. And so interestingly, what we found was that the DNA is bent pretty significantly. And so we think that the DNA bending is actually important for, first of all, opening up the duplex when it's searching. So think about this Cas9 enzyme searching through billions of base pairs, and it finds the PAM and it has to unwind. So it's very energetically unfavorable when you have all those base pairs to create an opening. But we think that this sort of bending helps create the opening and then stabilize this R-loop structure state. Okay, and so now in my lab, we've been working on a little bit of the kinetics of the Cas9. So it's actually surprisingly lacking in hardcore biochemical analysis of this particular enzyme. So you guys have been using it for all these cool things, but we're still not quite sure all of the specifics about how the enzyme itself works. And so we did this experiment where we looked at the cleavage rates of both of the active sites when we have DNA and magnesium initiating the reaction at the same time. So DNA was not there before. And you can see that there's this modest lag phase in the RubC domain. There's not so much a lag phase in the H and H domain. And then we did this cool thing where we did an R-loop formation measurement where we added 2-aminopurine into our DNA. And so 2-aminopurine, when it's base stacked, it has no fluorescence. When it becomes unwound, then you see the fluorescence. And so you can observe that change. And so we were actually able to observe this change. So I should note that this is all using stop flow and quench flow, so this reaction happens super quick. So we actually found that a majority of the product is already created after 5 seconds. So Cas9 will turn over all of its product in 5 seconds. And so what we found is that the R-loop formation rate is actually the rate limiting step. So it mimics more closely this RubC measurements. And so this is a global fitting of all 3 of those experiments. And so we have a model now where you have initial DNA binding that's slow. The R-loop formation is the rate limiting step. And then after R-loop is created, the chemistry is quite fast, on the order of 4 per second. And so that's my little introduction. I have a few other things to talk about. So we all love Cas9, but there's also all sorts of different types of CRISPR-Cas systems that I really know and love and have soft structures of. There's multi-subunit cascades and also type 3 complexes. So are there other genome engineering guys out there? Maybe. And then the last thing that I want to point out is now this is a more updated review of what we know about the hierarchy, the classification of these CRISPR-Cas systems, is that now there's more Cas9-like enzymes out there. So what are the potentials for those? And so with the bottom line being that, here's Baskin-Robbins, 31 flavors, is we have a lot of flavors of these systems. And there's still, I think, a lot to be explored in those areas. And so my take-home message for you is that Cas9 is a remarkable enzyme both structurally and functionally, and that understanding the basic mechanism of Cas9 is as important as using it for genome engineering applications. And I think that we can both inform and be informed by doing both the engineering aspects and also looking at it biochemically to understand how this enzyme functions. And with that, I'm done. Obviously, Jennifer Doudna, funding from these organizations. Some of these slides were provided to me by IGI, and then these are the people that worked on the kinetics experiments. Oh, and I'm not going to be around. I have to leave right after the session today. So here's my email, Twitter. Check us out. Contact me any way you want to. All right. So the session today, which was weird that I just told you about all the nitpicky details of Cas9, is exploring toxicology relevant uses of genome editing tools. And so our first talk will be by Dana Dolinoy from the University of Michigan, who will be telling us a little bit about piRNAs, which I actually love small RNAs, so I'm looking forward to hearing what she has to say.